this is our review for test 3. So I'll start with number 1. I think part A is pretty straightforward, and same with part B. So let's start with C. We have the integral from 0 to 1 of the integral from x to 1 of cosine of y squared, dy dx, right? So this first integral, if you try to do it, cosine of y squared, I'm not familiar with that one. So I'm sure there's a way to do it. I just don't know it. Seems pretty difficult without an extra y here for the substitution. So it seems like this is just the wrong order, right? If we switch the order, we should be able to do it then. But that also means graphing the region, right? So we're going from y equals x to y equals 1. So y equals x to y equals 1. Looks like this triangle here, right? And x is going from, 0 to 1. So this is 0. So if we want to go x first and then y, that should not be too bad. X is going from y, or no, sorry, x is going from 0 to y, right? So this is x equals 0 to x equals y. And then y goes from 0 to 1. 0 to 1. All right, so what has this got us? So the cosine of y squared is a constant. That can come outside. So we're doing the integral from 0 to 1 of cosine y squared, and then the integral from 0 to y of just, dx, and then dy, right? So the inside integral now is just y, right? Because it's the integral of dx is just x evaluated between 0 and y. So that gives us the y we need for substitution, right? So now u is y squared, du is 2y dy, multiply by 2, divide by 2, and we're all set, right? And in fact, when y is 0, u is 0. When y is 1, u is 1. So even the limits of integration don't change, which is unusual. That's a u. And the integral of cosine is sine. So we get 1/2 sine of 1 minus 1/2 sine of 0. But the sine of 0 is 0. So in the end, we just get the sine of 1 over 2. And the sine of 1 radian is about 0.8415. Or when you divide that by 2, you get about 0.4207 as an approximation. Right. So that's how that works. Again, I think D is pretty straightforward, but we can do that one too. So here we have the integral from 0 to pi over 2, and then 0 to cosine of theta, and we're integrating r cubed sine theta dr d theta. Okay, so first thing to note is that the first integral doesn't depend on theta, so we can take the sign outside here. Yep. So now we do the integral from 0 to cosine of theta of r cubed dr. and then we'll do the d theta. So this integral, again, pretty routine, just take the integral of r cubed as 1/4 r to the 4th. So sine theta, and then, yeah, r to the 4th evaluated at cosine theta, so cosine to the 4th. Right. So here's our next integral from 0 to pi over 2 of I'll do the cosine to the 4th first, and then sine theta. So pretty standard substitution. U is cosine theta. The derivative is minus sine theta. So we'll multiply by negative, multiply by negative. So now we get negative 1/4 the integral of u to the 4th du. Cosine of 0 is 1. Cosine of pi over 2 is 0. So, right, if that seems backwards, just switch them and multiply by negative 1. So now we're back to positive 1/4 the integral from 0 to 1 of u to the 4th du, which is 1 over 5, u to the 5, so 1 over 20. Okay, and then e is the interesting one because it's the sum of two integrals, and so that does not look all that easy. But let's at least see if we can make some sort of progress on that. So 0 to 3 square root of 2 over 2, and then the integral from 0 to y of the quantity x squared plus y squared to the 3/2. Now, you know that's probably going to become r to the 3. This is begging us to switch to polar coordinates, and I think that is the key here. dx, oh yeah, dx dy, not dy dx, right? And then the integral from 3 square root of 2 over 2 to 3 of the integral from 0 to square root of 9 minus y squared. That's also indication of polar coordinates, right? Because this is going to be a circle, or part of a circle. Right. So yeah, let's graph the region here. We didn't do it in part D, but it really wasn't necessary. Here, I think it's kind of critical that we graph this. Right. So 3 square root of 2 over 2, yeah, it's just over 2, right? 2.1 or so. So let's make this 1, 2, 3, 1, 2, 3. All right, so we're going from x equals 0 to x equals y. So here's x equals y equals x. And then y goes from 0 to right around here, 3 root 2 over 2, right? And of course, x will also be 3 root 2 over 2 here. Yeah, so x goes from 0. So this is, again, the upper half triangle here. I'll just highlight that part. All right, and then the second integral, I'll do in I'll do in green here. So this is going to be from 0 to square root of 9 minus y squared. You should recognize this as the circle, or at least part of it. Right. So here x is positive, right? And it's the circle of radius 3. So this would keep going to 3 here. Right. So x is going from 0 to that, except we're only going from y equals 3 square root of 2 over 2 to 3. So we don't include this part because that's less than 3 square root of 2 over 2. So yeah, we can include this region here as well. Okay, so this is just a sector. We're going from theta equals pi over 4 to theta equals pi over 2. Right? And r just goes from 0 to 3. So, oops, pi over 4 to pi over 2. There we go. And then r goes from 0 to 3. And the quantity we're integrating here is just r cubed. But remember, in polar coordinates, the Jacobian is r dr d theta. So that's my dx dy here. So it's really going to be r to the 4th, which in this case is not much worse. Right, and because the limits here don't even depend on theta, you can really just write this as the product, right? In fact, when you integrate with respect to theta, you just get, well, theta, pi over 2 minus pi over 4, and then 1/5 r to the 5th between 0 and 3. So looks like we get pi over 4 times 3 to the 5th, 243 over 5. And I don't see a way to simplify that. So yeah, 243 times pi over 20. Yep. So yeah, obviously by switching to polar coordinates, we made this integral much easier. Obviously, we could have evaluated this directly, but it would have been quite a hassle. So I think the way to go is switch to polar coordinates. Once you graph the region here, you can see that because it has this circular symmetry, it's best to switch to polar coordinates. Okay, so that's the first set of questions. Okay, so number 2 is also pretty straightforward. If you graph the region R, which I already did, we're going from x equals y squared on the left to x equals y plus 2 on the right. All right, so this is that bounded region. We're going from y equals -1 to y equals 2. So yeah, I think that's it. Just highlight the region here. So that's R. Oops. This is the region R. And we just want to do the double integral over that region of x times y. Okay. So, right, I would definitely think of this as a horizontally simple region. If you want to think of it as a vertically simple region, you kind of have to split it up into this region and then this region, and you're going to do the sum of 2 integrals. So yeah, so as a horizontally simple region, we're going to do dx, I don't need that much space, right? dx dy, where x just goes from y squared on the left to y plus 2 on the right, and y just goes from -1 to 2. So, right, so even if you didn't graph the region, you could just use the limits here. Pretty straightforward. All right, so the integral of x is 1/2 x squared. There's still going to be a y here. Can't forget the y. So yeah, x squared evaluated between y squared and y plus 2. Oops, that's supposed to be a y. All right, so yeah, y plus 2 squared minus y squared squared, y to the 4th, and that all gets multiplied by y. So yep, a little bit of algebra here. So this is going to be, let's see if I can do this. So y to the fourth times y, so y to the fifth. I'm sorry. This is just y. Yeah, I can't do that. All right, so y squared times y is y cubed plus 4y squared plus 4y, right, plus 4y. And then minus y to the fifth. Okay, so now it's just a straightforward definite integral. I'm sure you can all handle that. Okay, you get 45 over 4. So half of that is 45 over 8. Right? Yeah. So again, this is pretty straightforward, I think. So for number 3, we have the familiar disk of radius 2, except it's shifted to the right too, so it's centered at the point 2, 0. And, you know, if you convert to polar coordinates, you'll see that r for the circle is just going to be 4 times cosine theta. Right, so I think we did one like that before. All you're doing is plugging in x equals, r cosine theta, y equals r sine theta, and then just solving for r. So, yeah. So, yeah, if you do that with the equation of the circle here, so equals 4, and you convert that to polar coordinates, you get r equals 4 cosine theta. Anyways, right, so part A, I'm not going to do that because that's just the area of the disk, and because the radius is 2, you should get 4 pi. Right? Again, I would suggest you actually work it out, but it's very straightforward. Part B, not so much, right? Here we're integrating x dA, right? So if you will, it's like getting the center of mass, the x-coordinate of the center of mass. We just have to divide by m, which in this case is 4 pi, right? We're assuming the density is just a constant or just 1. Anyways, but we'll do that later. So yeah, the integral of x dA over the disk D. So I'm calling it disk D instead of region R, but same idea. All right, so in polar coordinates, we're going from either 0 to pi or negative pi over 2 to pi over 2. It doesn't matter. I like going from negative pi over 2 to pi over 2 just because I don't want to think of r as negative. Because if you're in the region where this is pi over 2 to pi, you should be over here somewhere. But you're only over here because, right, r is less than 0. It works out. But let's do it this way. Negative pi over 2 to pi over 2. And r goes from 0 to 4 cosine theta. And we're integrating x, which is r cosine theta. And then dA is r dr d theta, right? Okay, so minus pi over 2 to pi over 2 of cosine theta. And then the integral from 0 to 4 cosine theta r squared dr. So here's our first integral, and we just get 1/3 r cubed. So bring out the 1/3. And yep, so we're going to get r cubed, which is going to be 4 cubed is 64, and then cosine cubed of theta, times another cosine theta, which makes it cosine to the 4th of theta, minus 0, right? Okay, so bring out the 64. And remember, cosine is an even function, right? And certainly cosine to the fourth is even. So we can double this and just go from 0 to pi over 2. But cosine to the fourth. So we've worked this out before, right? You're just using the half angle identity, cosine squared. Well, let's do it properly then. Cosine to the fourth is going to be 1/2 times 1 plus cosine of 2 theta, but it's going to be, cosine squared of 2 theta. Right? And then you got to work it out again. So this is going to be 1/2 of 1 plus cosine of 4 theta. And then just multiply it all out, right? So essentially that's going to be the integrand here. And it's going to be a bunch of substitutions. And in the end, what you get is 3 pi over 16. Which means the 3's cancel. And then let's see, 2 to the 7 over 2 to the 7 over 2 to the 4 is 2 to the 3. So I think it's just 8 pi. Okay. So I realize I made a mistake here. This is cosine to the fourth. Right, it's cosine squared squared. So forget what I wrote here. This is cosine squared squared. Right, so it's 1/2 1 plus cosine of 2 theta squared. So it's 1/4 of, let's see, 1 plus 2 cosine 2 theta plus cosine squared of 2 theta. And that's the part we have to do again, right? So 1/4 plus, let's see, 1/2 cosine 2 theta plus, and then 1/4 of, so doing the same formula again, we're going to get 1, wait a minute, yeah, 1/2, 1 plus cosine of 2 times 2 theta, that's the 4 theta. All right, so this is the thing we're integrating here. And again, I would encourage you to work this out step by step. It's 1 over 8 plus 1 over 8 cosine to the fourth. So that's the thing you're integrating from 0 to pi over 2. Right. So that's the cosine to the fourth. All right, but yeah, so if you do that, that's where you get the 8 pi from. So part C, very similar, except you're integrating r sine theta. And in fact, from symmetry, we can see that this has to be 0 by just symmetry. Right? After all, y is negative on the bottom half and positive on the top half. Right? So yeah, they cancel out. You just get 0 here. Right? For part B, however, x is always positive, so you should get a positive number for part B. All right. Again, I would encourage you to actually work this out, as you would have to show your work. Right? And then part D, also pretty straightforward. You're just integrating r itself. So maybe we'll work that one out. Yep, so the integral of r dA. So we're still going negative pi over 2 to pi over 2, or 0 to pi, either way. And then the integral from 0 to 4 cosine of theta of r dr, so r squared dr d theta. Right? So when you integrate r squared, you just get 1/3 r cubed. And so when you cube 4 cosine theta, you get 64 cosine cubed theta. d theta minus 0, right? So yeah, these are pi over 2s. I don't know why I switched them to 3s. I was saying 1/3, I guess. Yep, so 64 over 3, the integral, and then cosine is even, so even though you cube it, right, it's still an even function. So we can double this again and go from 0 to pi over 2 of cosine cubed theta. Right. And this we can work out just by using the formula on the formula sheet. So yeah, so that's going to be, let's see, 3/4 sine of theta plus 1/12 sine of 3 theta plus c, but we're evaluating this between 0 and pi over 2, right? So sine of pi over 2 is 1, sine of 0 is 0, so you're just going to get 3/4 plus, yes, sine of 3 pi over 2 is negative 1. So this will be minus 1/12 minus 0, right? Okay, so I think we get times 3. So 8 over 12, which is 2 over 3. So I think we get 256 over 9. Okay, good enough. Okay, so I think 4 and 5 are pretty straightforward. So I'm going to do 6. Find the volume inside the cylinder of radius 2, right? So this is just the cylinder of radius 2, and the less than or equals means it's inside. So it's the solid cylinder, right? And in between the plane z equals 0, so that's just the xy plane. And y plus z equals 3. Let's see. So that's a, right, so that's a plane. Z is just equal to 3 minus y. So 1, 2, 3. And then this will be the x-axis, I guess. All right, so the xy plane, and then z is equal to 3 minus y. So that's this plane here. And again, it's just coming out of the screen here. Right. And then the cylindrical part of radius 2 is, didn't quite give enough space here, but I think it's this, right? So yeah, so what you're going to end up with is this little tree stump here. Right? So take a cylinder and slice it, diagonally like this. So this is still the plane, right? Z equals 3 minus y. And then we're above the disk of radius 2 in the xy plane. So that's the volume we're looking for, right? And, well, we can either think of this as a triple integral over the solid region Q, or a double integral over the region R, but we're integrating 3 minus y. In fact, that's just the first integral here, right? In the triple integral, z goes from 0 to 3 minus y. Right. Right. So, but yeah, because it's a circular region, we'll do the dy dx as polar coordinates. So we'll use cylindrical coordinates, right? Because it is a cylinder. So 0 to 2 pi, because we're going around the entire disk of radius 2. R goes from 0 to 2, right? And then z goes from 0 to 3 minus y. So this will be r dz dr d theta. Okay. So to do the first integral, you're just integrating 1 dz, so that's z. Right? Evaluated between 0 and 3 minus y, so we get r times 3 minus y, but y is r sine theta, and then minus 0, right? So dr d theta. So when you multiply that out, you just get 3r minus r squared sine of theta. So doing this integral gives you 3r squared over 2 minus 1/3 r cubed sine theta. But we're just evaluating between, oops, this is theta here now, between 0 and 2. So r is 2. So 4 divided by 2 is 2. 3 times 2 is 6, right? Minus 8 over 3 sine theta. And now it's about as easy as it gets, right? So 6 times theta. And then when you integrate minus sign, you get positive cosine. So 6 times 2 pi is 12 pi. And you get cosine of 2 pi, which is 1, minus cosine of 0 is 1. So 1 minus 1 is 0. So, yep, in the end, this is just 12 times pi. Okay, so that's the volume of this region here. 12 pi cubic units. Okay, number 7. So R is the planar lamina. So x squared plus y squared is less than or equal to 1. That's just the unit disk. Y is greater than 0, but less than square root of 3 times x. So this is the region R here. And in polar coordinates, it's a bit simpler. R just goes from 0 to 1. And theta goes from 0 to pi over 3. Right, so how did I know that this angle here is pi over 3? Well, the slope, right, is square root of 3. So that's the tangent of theta. What angle has a tangent of square root of 3? So the arctangent of square root of 3 is pi over 3, 60 degrees. All right, so that's part A. Part B, find the mass. So the mass is just the integral over that region of the density. I'm using sigma for density here. And since the density is 1, it's just the area of that region, right? And so the area of the region, well, let's work it out. 0 to pi over 3, 0 to 1 of r dr d theta. Right, so you're going to get 1/2 r squared again. Well, okay, so so this is pi over 3 times 1/2, right? It's pi over 6. I think that's the area. Yep. Of this region, right? Well, the area of the full circle would be pi, and this is just 1/6 of the circle. So, all right. So part C, center of mass. So we need x bar and y bar, and express in terms of r bar and theta bar. You don't have to do that, but for the x bar, it's just going to be 1 over the mass times the double integral over r of x times sigma times dA. Again, sigma is 1, so it's 1 over m, so 6 over pi times the integral, again, from 0 to pi over 3, from 0 to 1. But now it's going to be x, which is r cosine theta, r dr d theta. Okay, so with the 6 over pi, that's the 1 over m, we're integrating 0 to pi over 3 cosine of theta d theta times the integral from 0 to 1 of r squared dr. Yep, we can split this up because the limits are just constants. They don't depend on theta, right? Okay, so cosine of theta, the integral of that is just sine of theta. And when we plug in 0 and pi over 3, I think we just get square root of 3 over 2. We're going to get 1/3 r cubed evaluated between 0 and 1, so that's a 1/3. So 6 over pi times square root of 3 over 2 times 1/3. So I think it's just square root of 3 over pi. Okay, so that's x bar. And then we want y bar also. So again, 1 over m, but now we're integrating y. Sigma is 1. So 6 over pi times the integral, from 0 to pi over 3, and then the integral from 0 to 1 of r squared, sine theta. Right, y is r sine theta, dr d theta. Right. Okay, so integral of sine is negative cosine. And we'll just evaluate between pi over 3 and 0. And then we're going to get 1/3 r cubed again from 0 to 1, so that's just 1/3. So cosine of 0 is 1. Cosine of pi over 3 is 1/2. So 1 minus 1/2 is 1/2. Times 1 over 3 is 1 over 6. So I think we just get 1 over pi. So the center of mass, x bar, y bar, is just square root of 3 over pi, 1 over pi. Right, and if you convert to polar coordinates, again, just use the familiar conversion formulas. I think you get 2 over pi, pi over 6. Right? And so all that means is, when you look at the region up here, r is 2 over pi, so roughly 2/3. And it turns out that since this was pi over 6, pi over 3, pi over 6, so it'll be on this line. And then r is about 2/3, so maybe right about here, a little bit less. Right. So you can get it in terms of either x or y, so this is x bar and y bar, or in terms of r bar and theta bar. And that's the center of mass. It's also the centroid because the density is constant, right? So we call that the centroid. And for part D, find the polar moment of inertia. Right, so that's just the integral of r squared. Let's see if I can squeeze that in here. dA, and that's r dr d theta. So, of course, you're going to get r cubed now, dr d theta. So 0 to pi over 3, 0 to 1. So I think we just get the pi over 3 times 1/4, which is pi over 12. Okay, so that is the polar moment of inertia. All right, that's number 7. Number 8, just a series of iterated triple integrals, triple iterated integrals. So most of these are straightforward. Right, the limits are just constants, so I think you can work that out. B looks interesting because B has variable limits, so 0 to pi, and then 0 to sine of theta, and then 0 to r cosine of theta, r squared dz dr d theta. So this is in cylindrical coordinates. Yeah, so the first integral is just with respect to z. So you integrate z and you just get the r cosine theta, right? So you're going to get r cubed cosine theta, dr d theta. And then to do the inside integral here, with respect to r, you're going to get, 1/4 r to the 4th. So I think that's just sine to the 4th, right? Cosine to the 4th. So that's just a straightforward substitution, right? U is sine, du is cosine. So, and let's see, sine of pi is also 0. So you're integrating from 0 to 0. So of course you just get 0. Okay. Yep, and there's probably the reason for that is because of symmetry here. Or something like that. I don't know. Maybe not. Maybe not. Maybe you just get 0. All right. Yeah, I'll skip C, even though it has variable coordinates here. And this, to me, looks like convert to cylindrical, simply because of the 1 minus y squared. On the other hand, maybe not. Okay, let's do part C. I think part D might actually be easier, but let's see. So here we're going from 0 to pi again. Y goes from, x goes from 0 to pi. Yikes. Y goes from 0 to 1, and then z goes from 0 to the square root of 1 minus y squared, which I believe is just a cylinder, right? Yeah. So the first integral just gives you the square root of 1 minus y squared. All right. Now I realize this pretty much is going to be straightforward. We'll do the sine of x, and then this is just going to be y times the square root of 1 minus y squared. So substitution, right? So we just need a -2 here, and then a -1/2 equals, if I can squeeze that in here. So yeah, -1/2, and then the integral from 0 to pi. So before we do the sine x, this is just going to be the integral of the square root of u du. When y is 0, u is 1, and when y is 1, u is 0. So that'll end up being backwards here. And that'll probably cancel the -1/2, right? So, yeah, 2/3 u to the 3/2 evaluated between, we'll do 0 and 1 and make this a +1/2, right? So you just get 2/3 times 1/2, right? And then the integral from 0 to pi of sine x, I think that's just 2, but let's work it out, right? It's going to be cosine of x from pi to 0. Yep, 1 minus -1 is 2. So 2/3. Okay. And then, yeah, I think D, pretty straightforward. It looks like you do get like sine to the fourth or something. So if you get sine to the fourth, just work it out using the half angle identities, right? Or just plug it in a computer. All right. Okay, two surface area problems, 10 and 11. I think 11's probably the more interesting one. 10 is just a plane, and I know I worked one of those out already. So yeah, so here the surface is going to be z equals 9 plus x squared minus y squared, which I think is one of those hyperbolic paraboloids or something. I'm not exactly sure. In any event, surface area, if you remember, is going to be the integral of the square root of 1 plus the partial of f with respect to x squared plus the partial of f with respect to y squared dA. So we need the partial derivatives of this, right? So the fx is just going to be 2x, and the fy is going to be negative 2y, but when you square it, you're going to get positive 4y squared, right? So we'll get the limits of the integrals in just a second, but the integrand, the thing we're integrating, is 1 plus 4x squared plus 4y squared. And we could do dy dx, right? Yeah, so this is over the disk of radius 2, right? So, yep, y just goes from negative square root of 4 minus x squared to positive square root of 4 minus x squared, and then x goes from negative 2 to 2. If you were adventurous enough to work this out in rectangular coordinates, I think it's probably better to switch to polar coordinates in this case. So we're going from 0 to 2 pi since it's the entire disk, and r just goes from 0 to 2. And what we're integrating is 1 plus 4r squared r dr d theta. So using another u substitution, 1 plus 4r squared, du is going to be 8r dr. So we'll multiply by 8, divide by 8. It's an 8. Okay, and none of this depends on theta here, so that'll just be 2 theta. And then the integrand is going to be square root of u again. So when r is 0, u is 1. When r is 2, we get 1 plus 4 times 4. 1 plus 16 is 17, right? So we get 2 pi over 8, and then 2/3 u to the 3 halves between 1 and 17. Pi over 4 times 2/3 is pi over 6. And then this is just going to be, 17 to the 3 halves. So 17 squared root of 17 minus 1. So pi over 6 times 17 squared root of 17 minus 1. Whatever number that is, right? That's the surface area of that region of that surface, right? Okay. Right, number 12. This is a bit of a challenge. We have a hemispherical bowl of radius 5 feet filled with water 2 feet deep at the center. So here's your bowl. It's just, half of a sphere. And this is 5 feet deep, right? So 1, 2, 3, 4, 5. Say from 0 to 5. And there's going to be water in the bowl that's 2 feet deep. Right, so here's the surface of the water, and then the water just fills the bowl beneath it. So I guess this is also filled in here. All right. Well, let me at least highlight the surface here. There we go. All right. So what's the volume of water there? right? So, yeah. So it's a triple integral. So volume will just be a triple integral dv, and this is our Q. This is our region. So, yeah, there's a lot that we can really mess up on here, right? So the top surface here is just going to be a disk, and we have to figure out the radius of that disk. And the bottom surface will be the surface of a sphere, right? And it really kind of depends on where you want the origin to be. Do you want the origin to be right here at the bottom of the bowl? Or do you want it to be the center of the bowl if it were a complete sphere? And I would claim that this might be easier here, right? So if this is our origin, 0, 0, 0, right, then sure, the bottom surface here will be z is equal to negative square root of, let's see, the radius is 5, right? So 25 minus x squared minus y squared. Okay. Or if you're in cylindrical coordinates, it'll be negative square root of 25 minus r squared. Okay, so that's the bottom surface. The top surface is essentially just z equals negative 3, right? So here we're starting at 0 and going to negative 5, right? So, yeah, sorry, z equals negative 3. Right. So, yep, we want the entire disk, 0 to 2 pi for theta. R goes from 0 to, oh, we never figured out the radius here, but that's just trigonometry. So let me do the bowl again here. And then here's the water. All right. So if we think about this as our disk, right, what's its radius? So this is 5, this is 5, this is our radius. I'll call this little r here. And remember, it's 2 feet deep, so it's 3 feet up here, right? So this is a 3, 4, 5 triangle. Or just use the Pythagorean theorem, right? R squared plus 3 squared equals 5 squared. When you solve for r is 4. So we're going from 0 to 4. And then z goes from, well, negative square root of 25 minus r squared to negative 3. Right? And we just want volume, so we're integrating 1, r dz dr d theta. Okay, so that's what this would be in cylindrical coordinates. It's interesting to convert this to spherical coordinates. I don't think it would be that much trickier. But let's evaluate it this way, I guess, right? Nothing depends on theta, so we're going to get the usual 2 pi. We'll do the integral from 0 to 4. And then z, yep, so we're just going to get r, don't forget the r, times negative 3 minus negative square root of 25 minus r squared. dr, oh, we did the d theta part. That's just the 2 pi, right? Yeah, so before we integrate, let's simplify this. We're going to get r square root of 25 minus r squared. That's yet another substitution. And then minus 3r dr. So maybe we should split those up and do those separately. Yep, so we're going to get square root of u, where u is 25 minus r squared, so we need a negative 2, divide by negative 2, and then 0, so I think we go from 5 to 25 minus 16 is 9, right? Yeah, u goes from 5 to 9. Oh, wait a minute. If u is 25 minus r squared, when r is 0, yeah, that's 5. And when r is oh, it's 25, right? R does not include this u here, right? U is 25 minus r squared. There we go. When r is 0, u is 25. When r is 4, u is 9. Okay. And then let's just do the second part here. Minus 3 times 2 pi times the integral of just r, which is 1/2 r squared. Okay, so minus pi, this will be 2/3 u to the 3/2 evaluated between 25 and 9. And you can see the negative will make it a positive here. Minus 6 pi times 1/2 r squared evaluated between 0 and 4. Okay. So let's just make this positive 2 pi over 3. And then when you plug in the 25, you get 5 cubed is 125. And then 3 cubed is 27. So this is minus 3 pi times 4 squared is 16. All right, so 125 minus 27 is 98. And then 98 divided by 3. Is just 98 divided by 3. All right. And then 98 times 2 is 196. Yep. So 196 pi over 3. Right. Minus 48 pi. And 48 times 3 is 144. So 196 minus 144. 52. So 52 pi over 3. Okay. So that's the volume. Right. Again, the hard part are figuring out the bounds here, the limits of the integral. Again, just look at the geometry, right? Right. If you're tempted to think that the radius goes from 0 to 5, right, that's a pretty common mistake. That's the radius of the bowl, but it's not the radius of the surface of the water here. It only goes from 0 to 4 rather than 0 to 5, right? Or maybe it's more clear in the bottom picture here, right? The radius of this, the surface of the water here, is 4, not 5. So, yeah, be careful of that. Ooh. Okay, so 13 moment of inertia, 14 moment of inertia. I like this. I like doing the solid sphere here. So find the moment of inertia of the solid sphere. Again, in math, we call that a ball rotating around the central axis, let's say the z-axis, might as well, of uniform density, right? So if the density is uniform, so density sigma is just mass divided by volume. And we know the mass is capital M, right? So that should be a capital M here. Try that again. And the volume of a sphere, right, is 4/3 pi r cubed. Right. So that's our density. That's our constant, right? So the moment of inertia, Iz, is given as the triple integral over q. Q, of course, is the ball of, let's see, x squared plus y squared times the density dv. But the density is all just a constant, right? So that can all come outside. 3m over 4 pi r cubed. And while we're integrating, x squared plus y squared is really r squared, little r squared, right? dv. Okay, and this can be done either in cylindrical or spherical. Since we did the last problem in cylindrical, let's use spherical here. So we'll use spherical coordinates. Although I think it could be done either way. All right, so r squared, remember so if this is the z-axis, this is little r, right, and this is rho, and this is phi, so sine of phi is r over rho, which means little r is rho sine phi. You can just draw the triangle, or I think it's on your formula sheet. If not, it's something you can easily derive just by drawing the triangle here. So r squared is going to be rho squared sine squared of phi, and then dv is rho squared sine phi, d rho, d phi, d theta. Rho goes from 0 to capital R because that's the radius of the sphere. Phi goes from 0 to pi, right, because we're going from the positive z-axis to the negative z-axis. So the negative z-axis is just phi is equal to pi. And we're going all the way around the circle, so that's theta goes from 0 to 2 pi. Okay, so that's the setup. The rest is just some arduous integration. Although the theta integral is independent, so that'll just give us a 2 pi. But the rest, so 0 to pi, this is going to be sine cubed of phi, d phi, and then from 0 to capital R is rho to the 4th, d rho. So yeah, all three of these integrals are independent. The limits of integration, the limits of integration are all constants, and this is all just a product. So we can split it up as the product of these three integrals. And don't forget the constant here, 3m over 4 pi r cubed, right? All right, so 0 to 2 pi, that's just 2 pi. The integral of sine cubed from 0 to pi is just 4 over 3. Again, you should probably work it out using the formula on your formula sheet. Not bad. And then rho to the 4th, you get 1/5 rho to the 5th, so 1/5 r to the 5th. All right, so now it's just a bunch of arithmetic here. So let's see. Well, let's cancel this 4 and this 4 cancel. This 3 and this 3 cancel. So what are we left with? 2 pi. Oh, the pi's cancel, of course. Pi divided by pi cancels. So we have 2m on the top, r cubed on the bottom, and then we have r to the 5 over 5. So we get 2m r squared over 5. And this is indeed the moment of inertia about any central axis. We just use the z-axis for convenience here, of a ball of mass m and radius r. So this is a formula usually given to you in a physics book, right? But this is where it comes from, right? This is how to, well, let's put it this way. This is one way to evaluate it, right? And I know in your physics book, it probably tells you to evaluate this, right, as the triple integral of r squared dm. But dm, right, is really just the density times the volume, right? So sigma times dv. And I know most books use rho for density, as long as you don't get confused with density and distance. So two different rhos. We talked about that many times already. Okay. So yeah, physics books will write it in terms of m, in terms of the mass, but you just, work it out as density times volume in most cases. All right, so now we get to the vector calculus part. This is starting in chapter 15. We want, the divergence and the curl for these vector fields here. I think part B is pretty straightforward. Let's do part A. Right, so the divergence of this vector field is just partial of m with respect to x plus partial of n with respect to y plus partial of p with respect to z. Right, this is your m, n, and p. So writing it all out in its detail, derivative of cosine plus the y partial of sine plus the z partial of 3z squared. So I think we're going to get negative sine x plus cosine y plus 6z. Right, so that's the divergence, right? Remember, no I, j, and k. The divergence is a scalar function of x, y, and z. All right, so for the curl, again, I prefer to think of this in terms of the determinant, I, j, k, and then these are the partials with respect to x, y, and z, respectively, and then the m, n, and p, cosine x, sine y, and then 3z squared. Sorry, that's supposed to be vertical for the determinant. So for the first determinant, you're taking the partial of 3z squared with respect to y, well that's 0, and then the partial of sine y with respect to z is 0. And you can see these are all going to be zeros here, right? So the curl is 0. It's 0i plus 0j plus 0k, which is just the 0 vector. Okay. Yeah, right. So, with respect to x of z, with respect to z of x, and so on, right? So these are all going to be zeros here. So the curl is 0, which tells you what? It tells you that f is conservative. But we didn't need to know that here. But that might happen, right? This might be applicable if we're doing, say, a line integral, especially if it's a closed curve. If it's a closed curve, the integral is 0. But if it's not a closed curve, then you just evaluate it at the endpoints using the fundamental theorem of line integrals. All right, so that's divergence and curl. And part B is even easier because notice there's no z in either the m, n, and p here. Okay, so 16 I'm hoping is a quick one. R is just essentially the position vector. Right? We can think of this as a vector field, of course, if you want to call it capital F. But it's just xi plus yj plus zk, right? And r, little r, without the vector, is just the usual distance from the origin. Oh, yeah, so you have to be careful here, right? We used to call this rho. Now we're calling it little r. So just be aware of that we're not using rho anymore. We're using little r for the distance from the origin rather than the distance from the z-axis, which is what we used to call little r. So the book is doing this little switch on you in some cases, and it's very subtle, and they don't even mention it. So you got to be careful what your little r is, right? Because it really depends on the situation here, right? But, I mean, most physics books will use r for this distance, right? And even math books too will switch to little r. It's only in the context of spherical coordinates when you're talking about rho. So yeah, just be aware of that, right? So anyways, the first question is, what's the gradient of r? Right, so remember what gradient is. It's just The partial of r with respect to x is the y component, the I component, the x component. Partial of r with respect to y for the j component, and partial of r with respect to z for the k component. And in each case, you're just going to get, let's see, I think it's x over square root of x squared plus y squared plus z squared times I, plus y over the square root of x squared plus y squared plus z squared times j. Likewise for z. Yeah, that's y squared, z squared. Okay. Right, so this is actually just r, the vector, divided by r. And you can think of that as the unit vector in the direction of r, right? So if this is your x and y axes, let's say the distance to this point is r, right? So the vector r would be the vector from the origin to that point. Right? However, the unit vector r would just have length 1. Okay, so when you see r hat, that's the unit vector in the radial direction. Okay, right, so that's all the gradient of r is. Right. What about the divergence of the vector r? Right. So that's the usual partial with respect to x of the I component is just x, right? Plus the partial of y with respect to y, plus the partial of z with respect to z. And these are just 1, right? 1 plus 1 plus 1 is 3. So you just get the number 3. And finally, the cross product with the vector r. So again, setting this up as a determinant. And these are the partial derivatives. This is just x, y, and z. And you can see that when you take the cross terms, the partial of z with respect to y is 0, and so on. So this is also the 0 vector. Right? Yeah. Which means this vector r is conservative as a vector field. This vector field is conservative. Right. In fact, any vector field that only depends on the distance from the origin, right, is going to be conservative. Right. This is useful in physics because you get what are called central forces. Right. Gravity is a central force. It pulls inward. Right. So you might get a minus sign, but it's only going to be So it's going to be proportional to minus r over r cubed, or minus, right, the unit vector r over r squared. So it's an inverse r squared force. But you can at least hypothetically dream up of forces that depend on, say, 1 over r cubed, or 1 over r to the 4th, or 1 over square root of r. But gravity is definitely inverse r squared, and that's been shown experimentally to a very fine degree. Very, very small experimental error there. And number 17, determine whether the vector field f is conservative, and if so, find a potential function. So m is e to the y plus y e to the x, and n is x e to the y plus e to the x. And there's no k component, so the condition for conservativeness is the partial of n with respect to x equal to the partial of m with respect to y. Well, let's do first the partial of n with respect to x. Again, that's my little notation for that. So with respect to x, you just get x e to the y plus e to the x. Oh, sorry. The partial of that is just going to be e to the y plus e to the x. And now for the partial of m with respect to y. So m is e to the y plus y e to the x. So yep, you get e to the y plus e to the x. Same thing. So these indeed are equal. So f is conservative. And now we can find the potential function by just integrating m with respect to x. So the integral of e to the y plus y e to the x with respect to x is going to be x e to the y plus y e to the x plus possibly some function of y that we don't know about yet. So to find h1 of y, now we just integrate n, which is x e to the y plus e to the x, but now with respect to y. And in that case, you get x e to the y plus, yep, y e to the x. Same thing, plus some function of x, but for these to be equal, they have to be a constant. So your potential function is just x e to the y plus y e to the x plus some arbitrary constant. And that's it. That's 17. Okay, so I think the rest of the practice test is mostly line integrals. All right. So number 20, evaluate the line integral of r. And remember what r is. We just did that not too long ago, is xi plus yj plus zk. And c is just a unit circle going counterclockwise, the usual orientation. Right? That's the positive orientation. If you go clockwise, that's considered negative. Right? All right, so yeah. Right, so let's just work this out, right? dr, of course, is just going to be dxi plus dyj plus dzk. And when you take the dot product, you're just going to get x dx plus y dy plus z dz. So that's just another way to write this. And the circle, well, we have to parameterize it. So r of t, again, don't get confused with this r, but that's why I wrote it this way. So we're done with the vector field r. Yeah, cosine and sine. And t goes from 0 to 2 pi. Right? Oh, and I guess we need a z component here. I guess that will have to be 0. So yeah, so we're still going from 0 to 2 pi for t. And then r prime, because we need that for the dr, is just going to be negative sine of t cosine of t, and the derivative of 0 is 0, right? So the integral from 0 to 2 pi of x, which is cosine of t, times the derivative of x, which is negative sine of t, plus y dy, y is sine of t, dy is cosine of t, and then z is, well, 0, and dz is also 0. So you're just doing the integral from 0 to 2 pi of 0, which of course is 0. Oops, looks like a 6. There we go, 0. Right? And maybe this should not have been a surprise that we get 0. After all, right, the vector r looks like this. And the vector dr, well, dr is the tangent vector, right? It looks like this. So those have to be orthogonal, which means the dot product here is 0. So of course you're going to get 0, right? In retrospect, that had to be the case. But again, I wanted to work it out step by step here. All right, maybe we'll do 21, because it is rather conceptual here. We have C, any open curve that lies on the sphere. So here's my sphere. It looks like the radius is C here. That's unusual. You know, we could use capital R, we could use, little a. The book likes to use little a I like to use capital R. And now we're using c, just to emphasize that it is a constant, right? So imagine some curve on the sphere. It could just be the equator. That's a curve, right? But you can imagine any curve on the sphere here, right? Starting at one point and ending at another point. So that's my curve. Oh, maybe I shouldn't use c here. Capital C for the curve. Okay. And here we want to prove that over that curve, rdr, the line integral of rdr is 0. And in some ways, yeah, we just showed that, but that was for the circle, not a curve in the sphere. The circle is a closed curve. This is not a closed curve, right? This starts at one point, say at point A, and ends at point B. Okay, so not the same situation, right? However, right, we are in the following situation here, that at any point on the curve, when you take the vector r to that point, and right, you're going to be on the sphere at this point, your dr will be tangent to the sphere, and therefore necessarily also tangent to the curve. And so you should get a dot product of being 0 again. R dot dr should be 0. Okay. But let's work it out, right? Let's just parameterize this curve. Well, since this could be any curve, I don't think we want to give a specific parameterization. I'll just call them x, y, and z as functions of t, right? And then dr would just be, again, dx as a function of t, dy, dz. So, yep, when we work out the line integral here, we just, again, get x dx plus y dy plus z dz. Oops, I forgot the z. Dz. Okay, right? Or if you're integrating from, say, a to b, x, and then we just multiply by, the derivative of x. That's not a dot product, right? I'm just doing x times the derivative of x. Right, so maybe I'll just call it x prime. And then y times y prime. Right, and then z times z prime. dt, right? So yeah, t just runs from a to b, right? In other words, r of a is the point A as a vector, and r of b is a point B as a vector from the origin. Okay, so here's the trick, right? If we think about this integrand here, this looks an awful lot like, oh, sorry about that. There we go. Yeah, this stylus tends to do that with this little button here. Anyways, so think about this as a dot product here, right? I mean, it is r dot dr, right? But it's also the derivative, right? If we take the derivative of just x times x, or x squared, right? And then y times y squared, plus z squared, right? Because when you take the derivative of this, you just get 2x times x prime. Oh, so we don't have a 2 here, so yeah, we'll have to cut that in half then. Right? So yeah, take out the 1/2. But then this is just the integral from a to b of the derivative of, well, x squared plus y squared plus z squared is c squared. But c is a constant, right? C is the radius. So, of course, this is just 0. And so you get 0, which is, well, we knew that already. We just had to show that using this calculation here. Okay. So, yeah, so that's how the proof goes. Not easy, right? Especially when you're not thinking about, right? If you're struggling with how to integrate this, right? It's kind of the reverse chain rule here with the x squared plus y squared plus z squared. So that's that's, that's how to do that. It's a technique that, once you get used to it, it comes up a lot. But, so here it is, maybe for the first time. Maybe you're seeing this for the first time, but all right, enough of that, right? So not a lot of proofs here, but this I think is a routine one, but one that does involve this little bit of a trick to calculate this sum here. I was going to skip 22, but I think this might not be quite as simple because we're going clockwise instead of counterclockwise, right? So it is just a circle. Oh, sorry, that's not the center here. Let me get rid of that little point. Radius 1, because it's the unit circle, right? But we're going from the North Pole, 0, 1, to the East Pole, if you want to call it that, 1, 0. But yeah, we're going clockwise. So that's my point A, point B. So, yep, the parameterization for that, the easiest way to do that is just to use a sine of t for x and cosine of t for y, which I know is usually backwards. We usually do cosine and then sine, but that goes counterclockwise. So if you're going to do that, you're going to have to somehow run backwards, right? You're going to have to do a, right, from 1 to 0 instead of 0 to 1. Or in that case, from, pi over 2 to 0 instead of here, it's 0 to pi over 2. So, right, so yeah, by going clockwise, we'll just do sine and then cosine, right? And then the derivative will just be cosine sine. Or, sorry, cosine negative sine. All right, so now we can do the line integral, right? We're going to do the vector field f is just x, y. In terms of t, that's just going to be sine of t, and then sine times cosine, right? And we already know what dr is. It's cosine negative sine, right? So the line integral of this vector field is just the definite integral from 0 to pi over 2 of, and then let's write this out, sine of t sine cosine, and then the dot product with cosine negative sine, and that's my dr. Right, so this is my dr, and this is my vector field f expressed in terms of t, and then you just take the dot product, right? All right, so for the dot product, we're going to get sine times cosine, and then plus, or in this case minus, sine squared times cosine. Okay. Yeah, so this should just be a pretty basic substitution. If we think about this as sine minus sine squared times cosine, let u be sine minus sine squared. Or no, u is just sine, sorry. Yeah, u is just sine, and then du is cosine, dt. Right? So this is my du, and then this will be u minus u squared. Going from 0 to 1, right? Sine of 0 is 0, sine of pi over 2 is 1. Right? So we're just going to get 1/2 minus 1/3. Which is 1 over 6. Okay. Yeah, this had to be done directly, right? We had to just work this line integral out directly. The vector field here is not conservative, and you can just check that. Partial of n with respect to x minus partial of n with respect to y is not 0. It's y, right? So it's not conservative, so we cannot use the fundamental theorem of line integrals here. Just do it directly. Right, next one, 23. So this is a vector field in space, right, instead of in the plane. So this vector field is yz, xz, xy. And C is the line segment from 0, 0, 0 to 2, 4, 6. So when you're parameterizing your line, how about just, how about 2t, 4t, 6t? And that way, t just runs from 0 to 1, right? And your derivative is just 2, 4, 6. Right, well, yeah. dr will be that times dt. Okay. Right, but do we need to parameterize this at all? Is this vector field conservative? Well, let's check. Right, take the curl, and if we get 0, then we can use the fundamental theorem of line integrals. xy. All right, so what do we get? We get x minus x. Okay, that's 0. We get y minus y is also 0, and z minus z is also 0. So yeah, we get 0, 0, 0. So it is conservative, right? So we can find the potential function, oops, x, y, and z here, just by integrating m dx. So I think you just get x, y, z, plus some function of y and z. And when you integrate n dy, you also just get x, y, z, plus some function of x and z. And finally, when you integrate, oops, equals p dz, you get x, y, z, plus some function of x and y. And now it's pretty clear that all three of these functions are just a constant. So your potential function, it couldn't be easier. It's x, y, z plus a constant. So, yep, to do the line integral, we can just use the fundamental theorem of line integrals, evaluate the potential function at the two endpoints. So xyz is just 2 times 4 times 6 minus 0 times 0 times 0. So you just get 48. Right? Now we could have done this directly, right? It wouldn't have been that much more difficult. Rather than take the curl and then integrate to get the potential function, we could have just done this pretty directly here. But you get the same answer either way, 48. So I decided to do it using the fundamental theorem of line integrals. So this is the fundamental theorem of line integrals, FTLI if you like. Yep, so it comes in very handy when your vector field is conservative. If the vector field was not conservative, we would have no choice. We would have to do it directly. Okay. Now let's do 24 as well. So this is just another line integral, but here it's expressed in differential form, right? So instead of writing it as f dot dr, we're just writing it as 2xy dx plus x squared plus y, sorry, x squared plus y squared dy. And y is just the parabola 4 minus x squared from the point 2, 0 to the point 0, 4. 2, 3, 4, 1, 2. Yeah, so the usual parabola, right? So this is not a closed curve. We're going from 2, 0 to 0, 4. Right? So as far as your parameterization goes, we might as well just use x equals t and y equals 4 minus t squared. But right, this is a happy coincidence here because this works out. If you take dy, you just get negative 2x dx, right? So we can use that here. We can just think of, since x is t, we're just going from, we're going from 2 to 0. Yikes, that's backwards, right? You can't have 2 less than 0, can you? Well, okay. I mean, that's gonna look weird, but it's gonna work out in the end. So this is going to be the integral from 2 to 0 of 2 times x times y. Y is 4 minus x squared dx. And then x squared plus y squared. Yeah, x squared plus y squared, but y is 4 minus x squared squared. And then dy is negative 2x dx. Right? So remember, if this looks weird because it's x, remember x is just t. So I could just as well use t's here instead of x's. So I don't know why I'm using the same color here. When I'm working this out, I should use yellow. All right, so what is all this mess here? This is going to be 8x minus 2x cubed times dx, right? Plus x squared plus 16 minus 8x squared plus x to the fourth, times negative 2x. So we'll have to do that as well. Oh, wait a minute. It's the whole thing, right? So the x squared is also, yeah, times negative 2x. All right. 2 to 0, right? So the 8x minus 2x cubed, that's on the outside. And then we're going to get, let's see, this is just x to the fourth minus 7x squared plus 16. And then multiply that times the negative 2x. You're going to get negative 2x to the fifth plus 14x cubed minus 32x. Yeah, minus 32x, right? dx. All right, so at this point, we can simplify this a little bit more here. So negative 2x to the 5, there's no x to the 4s. 14 minus 2 is 12x to the 3, and then negative 32 plus 8 is negative 24x. All right, so you work all that definite integral out. And you should get 64 over 3. Okay. Yep. Now, we didn't check if this vector field is conservative. So this is partial of n with respect to x and x. So that's just 2x. Partial of m with respect to y is also 2x. Yeah, as it turns out, it was conservative. So we didn't have to do it this way. We could have just found the potential function and then plugged in the endpoints. The potential function is going to be, let's see, x squared y plus, and then when you integrate this with respect to y, you get 1/3 y cubed, right, plus a constant. So I worked that all out pretty quickly, but when you plug in the 0, 4, you're just going to get 64 over 3 plus c. And when you plug in 2, 0, you get 0 plus c. So when you subtract, 0, 4 minus 2, 0, you get 64 over 3. So that would have been another way to do this. I did this rather quickly, but yeah, you get the same thing either way. So it turns out this was conservative. Maybe we should have checked that first and then saved us the trouble of doing this directly, but no, it doesn't hurt to do it directly as well. So either way. Yeah, so I'm going to skip 25 because that one it's similar enough, right? It's pretty similar. It's still a line integral over a curve, right? So 26 is, well, you can say that this is also similar as well. But we're dealing with a curve in space here. So this is in 3 dimensions. So we want to evaluate this line integral here. And this is just the line segment, so if we have to parameterize it, so yeah, how about 1 plus 3t, 0 plus 2t, and then, so this will be 1 minus 2t. T goes from 0 to 1. Right? Again, I did that fast, but you just use your initial point and your final point here. 1, 0, 1 for your initial point, 2, 2, negative 1 for your final point. And yeah, so dr is just 3, 2, negative 2. So that's our direction vector, if you like. So I'm not going to check if this is conservative. I'm just going to do it directly, I think. I don't know if it's conservative or not. You have to take the curl, right? All right, so let's just work this out here. Oh, but it would be, you know what? It would be easier if it is conservative. All right, let's check. Take the curl. See if we get 0. Right, so we get negative 2y, and then with respect to z, we just get minus x. So it doesn't matter what the rest is. This is not 0. Okay, so it's not conservative. Right? In other words, this differential form is not exact. For those of you who have had differential equations, you might notice the connection between exact differential forms and conservative vector fields. Kind of the same thing, right? Right, so yeah, we have to do this directly, right? All right, so definite integral from 0 to 1, x times y is 1 plus 3t times 2t, and then dx is just 3, right? Plus x times z, 1 plus 3t times 1 minus 2t, times dy, which is 2, and then minus y squared. That's 2t squared, and then dz is just negative 2. All right, so not a difficult definite integral to work out. I mean, just multiply it all out, work it out. So I think this becomes 6t squared plus 2 dt, and that ends up being 4. So the answer is 4 for number 26. But yes, this we had to work out directly. Luckily, it wasn't that hard, particularly because it was a straight line. But even if it's a curve and we get like t squared or t cubed or sine of t, hopefully the integral will work out pretty simply, as it does here. All right, 27. This is going to be the line integral. I'll just copy this down here. Of x squared minus y squared dx plus 2xy dy, kind of the reverse of what we had earlier. And c is the closed curve r equals 1 plus cosine theta. So that's the cardioid. Let's graph that out. So I think you get 2 here, 1 here. Yep. So it's your usual heart. Right, so it is a closed curve, and this should be symmetric here. Let's see if I can fix that. Oh, gosh. All right. Well, all right. That's better. All right. So if this vector field were conservative, then because it's a closed curve, presumably we're going counterclockwise, right? Then we would get 0. So is it conservative? Partial of n with respect to x is 2y. partial of m with respect to y is negative 2y. So they're not equal. So this is not conservative, not exact, or conservative. So no, we probably don't get 0 then, in that case. However, because it's a closed curve, we can also use Green's theorem instead, right? Or, I mean, or we could work it out directly, but I think Green's theorem probably makes it a little bit easier here. Right, so Green's theorem just says that this line integral here can be calculated as the double integral over the region R of partial of n with respect to x minus partial of m with respect to y, dA. And we already know what that is, right? This is 2y minus negative 2y, so this is 4y. And, yep, we'll use polar coordinates here. So well, we can bring out the 4. That's a constant. And then y is r sine theta. And then dA, remember, is r dr d theta. R goes from 0 to 1 plus cosine of theta. And theta goes from 0 to 2 pi, since we're going all the way around. All right, so let's just work this out. 4 times the integral from 0 to 2 pi. So we're going to get r squared, right? The integral of r squared is 1/3 r cubed. But we're evaluating that between 0 and 1 plus cosine theta. Right? So we're going to get 4/3 times the integral from 0 to 2 pi of 1 plus cosine theta, the whole thing cubed, times sine theta d theta. So I think a substitution is in order here. Let's just do 1 plus cosine theta will be our u. Then the derivative of that will be minus sine theta. So we need a minus sign here. Maybe I should use red. And then we'll bring out the negative sign here, right? So this is your du, and this will be u cubed. Okay, so now we're going to get negative 4/3 times the integral of u cubed du. So let's see, if theta is 0, cosine of theta is 1, so u is 1 plus 1, which is 2. And if theta is 2 pi, well, cosine of 2 pi is also 1. 1 plus 1 is 2. Oh, so, yeah, this has to be 0. Right, you get 1/4 u to the 4th, but when you plug in 2 and 2, you get 16 minus 16, which is 0. Okay, so we do get 0, even though this was not conservative, remember? If it was a closed curve of a conservative vector field, you would always get 0. In this case, we happen to get 0 but just by coincidence, right? This has nothing to do with the fact that this is that this is a conservative vector field. In fact, it's not conservative. We checked that, right? So, yeah, just because it's not conservative doesn't mean you're not going to get 0. It just means you're not likely to get 0. It's right. So this is one situation where we happen to get 0 anyways, but not because of the fundamental theorem of line integrals. It's because of Green's theorem that we end up with 0. Right. So here's the thing, right? If C is any other curve, like if you take a square here, counterclockwise, right, and you did the line integral over that, you're not going to get 0. You're almost not likely to get 0, right? Almost never, right? So if you take a circle, if you take any other closed curve, because the vector field is not conservative, you're not likely to get 0. You will in some cases, right? In some weird cases where you get this coincidence here. So be careful of that. You do get 0, but it has nothing to do with being conservative and being over a closed curve, right? So we could have worked this out directly as well. It would have been, it's probably, yeah. Well, you'd have to parameterize this curve, right? And you can take theta to be t, but then getting the x and y might not be that simple here. So probably best to just do this using Green's theorem. All right, last one. 28. Evaluate the line integral of, I'll write it out again, negative y to the n dx plus x to the n dy. And so n is just a positive integer, right? So 1, 2, 3, 4, and so on. And c is the unit square with vertices at these four corners, right? So we just get 0, 0, 1, 0, 1, 1, 0, 1, and 0, 0 again. So we're going counterclockwise, right, over these four corners. That's a 0. Okay. Yeah, this I think is begging for Green's theorem, right? Simply because, well, first of all, I don't think this vector field is conservative. You can check that. Right, you get n x to the n, right, plus y, and y to the n. So not conservative. However, it is a closed curve. So unless you want to parameterize all four of these line segments, let's use Green's theorem again, which just says that we're doing the double integral over the region R. R is the square, of course, or inside the square, of partial of n with respect to x minus partial of n with respect to y. Yep, so that's going to be nx to the n minus 1 minus negative ny to the n minus 1. So I think we can pull out an n here. Yeah, so we just get x to the n minus 1 plus y to the n minus 1. And because this is the square, y is going from 0 to 1, x is going from 0 to 1. And we could do it either way, vertically simple, horizontally simple, either way. So when we integrate this with respect to y first, we're going to get x to the n minus 1 times y plus 1 over n minus 1 times y to the n, right, evaluated between y equals 0 and y equals 1. So when y is 0, you get 0. When y is 1, you just get x to the n minus 1 plus 1 over n minus 1, right? And now we do the integral with respect to x. Oh, I'm running out of space. So I think I have just enough space to do this. So when you integrate this with respect to x, you get 1 over n minus 1 times x to the n plus x over n minus 1. Oh, that was the integral, sorry. So now just evaluate it between 0 and 1. Okay, so we get n over n minus 1. So we get 1 to the n plus 1. So we get 2n over n minus 1. Maybe I'm missing something here. Because I don't think that's right. What did I do wrong? Oh, I know what I did wrong. I forgot the power rule. Right? It's x to the n plus 1 over n plus 1. So if you're integrating x to the n minus 1, you just get x to the n over n. So these n minus 1s here should have just been n's the whole way. Okay, so get rid of the n minus 1. Here and here. and here, and here, and finally here. Yeah, so it's really n over n, which is 1. So the answer is 2, right? 2n over n. Right, n is not 0, of course. But so n could be anything other than 0. It doesn't have to be a positive integer here. But that's the situation we're in. So the answer here is 2, right? Regardless of what n is. As long as n is not 0, actually, I think you get 2. Although I'm not sure about -1. If n is -1, remember you have to worry about the logarithm there. So I'm not 100% that works, but so I know it works for any n not 0 and not -1. Right. If n is 0, if n is 0, you just get dx plus dy. So I think that actually works as well. It doesn't matter, right? We're not worried about n equals 0 or -1 or -2, right? So n is a positive integer, so we know it works here. So that's just the power rule for integrals. And, you know, again, I messed up because I divided by n minus 1 instead of n. All right. I think that's it. So good luck.